Here's the difference between chapter 10 and chapter 11. Chapter 10 was about counting. Chapter 11 is about probability. They're related because you have to be able to count to do probability. Now you guys, I'm sure, have a feel for what probability is. If you read the definition in your text, it'll simply say the likelihood that an event is going to occur. Okay, how likely is it that it's going to rain today? That's a probability. How likely is it that I'm going to assign you homework today? It'd probably be pretty high because I've assigned you homework almost every day. Okay, I'd probably have a pretty high probability. What's the probability that I'm going to stand on 2 feet and vertically jump over the tables in this class? Oh, that'd be a very low probability. I haven't done that yet, and I doubt that I'm still capable of that. In fact, I'm pretty sure that I'm not capable of it. Not 100% sure, but pretty sure that I'm not. So there are some key words dealing with probability that we need to be familiar with. Okay, one word is the word experiment. Your book says this, and then we'll try to make some sense out of it. An observation or measurement of a random phenomenon. That's an experiment. What does that mean? Well, experiments are what we're finding probability in the context of. For example, I might say, roll a die 10 times and find the probability of rolling a 3 2 times out of those 10. Well, the experiment would be rolling the die 10 times. Okay? Flip a coin 6 times. What's the probability of getting 3 heads? Well, the experiment would be flipping the coin 6 times. So it's the phenomenon that you're looking at. Okay? So you don't need to write down a big definition, but just know that when you find a probability, there's some sort of experiment attached to it. Okay? Now, when you do an experiment, then you're going to have outcomes. An outcome is a possible result of the experiment. Let's assume that I roll a 6-sided die. Give me one possible result.
6.
You could roll a 6. That's an outcome. Okay, you could roll a 3, or 2, or 1, or 4, or 5. Now, the most important phrase that you're going to learn here in the next few minutes is probably this one. Sample space. So I'm going to say this many times today and throughout this chapter. If you've got a probability problem that you don't know where to start with, then start with the sample space. The sample space is a list of all outcomes. If I roll a die, the sample space is 1, 2, 3, 4, 5, and 6. If I flip a coin, the sample space is I could get a head or I could get a tail. In other words, it's everything that can happen. That's your sample space. On the next test, as far as your grade is concerned, what's the sample space? Well, the sample space is A, B, C, D, or F. It's everything that can happen when you take a test, at least in this class. So a lot of times by listing out the sample space, your probability problem gets more understandable. So we'll do that quite often. Okay, an event, if you look at the technical definition, it's a subset of the sample space. But for us, let's think of it this way. An event is what we find the probability of. For example, if I'm rolling a die, I could ask you what's the probability of rolling a 3. That's an event. Now, you can see why the definition subset of the sample space works, because 3 is a subset of 1, 2, 3, 4, 5, and 6. But it doesn't have to be that straightforward. I could also say, what's the probability of rolling an even? In that case, I'm looking at 2, 4, and 6, which is another subset of the sample space. So we find the probability of events. Okay, now there are two types of probability. There is theoretical probability, and there is empirical probability. There's a slight difference between the definition of the two. To make sense out of that slight difference, I want to tell you another way that we can decide whether we have theoretical probability or empirical probability. With theoretical probability, you don't have to actually perform the experiment. No experiment performed. For example, if I said to you, what's the probability of rolling a 3 when you roll a 6-sided die, you would say to me what?
One, 3.
How many sides of the die are there?
6.
There are 6.
I thought you said 3-sided die.
Okay, so there'd be 1 out of 6, right? So did you have to actually go roll the die 50 times and see how many times a 3 came up to figure that probability? No. You knew by the nature of the problem what the probability was. That's theoretical probability. Okay? So the definition actually goes like this for theoretical probability. P parentheses E stands for the probability of an event is equal to the number of ways the event can occur on our last problem. What's the probability of rolling a 3? There's only one way I could get a 3. The number of ways the event can occur over the total number of possibilities. And when I roll a 6-sided die, the total number of possibilities is obviously 6. Now we don't usually write out the formula that way. We usually write it out this way. The number of ways an event can occur we call N of E. And look, the total number of possibilities up here, we said that the sample space listed all the possible outcomes. So the total number of possibilities is your number of items in the sample space. So we usually call that N of S. So the definition of theoretical probability is the number of ways the event can occur over the number of items in the sample space. Okay, well, if I change the problem, and let's say this time we're not going to find the probability of rolling a 3. Let's say the problem is I'm going to take this chair right here and toss it in the air 15 feet, which would be difficult to do. And I want the probability that it lands on all fours, which you can't see in Metro, but that one actually did. Well, that's not so easy to inherently see the probability of, is it? It's not like 1 out of 6 rolling a 3. So the only way for me to really figure that probability is to actually toss this chair into the air, maybe, I don't know, 25 times, 50 times, whatever, and see how many times it lands on all 4. So I'm actually performing the experiment. That's empirical probability. So with empirical probability, the experiment is performed. So how would I figure the probability then? Would be the number of times the chair landed on all fours over the number of times I performed the experiment. That is the very definition of empirical probability. The probability of an event is equal to the number of times event E occurred divided by the number of trials, the number of times I did the experiment. So for the rest of this section, we're going to find both some theoretical and empirical probabilities. Some will be easier than others. We're going to talk about what odds are. And in the process of doing all that, we'll discuss something called the law of large numbers. Okay, so let's go to page number 580. And I want to start with example 3. And I think that'll give us a good illustration of kind of how we want to approach a probability problem when we're not for sure where to go. So let's look and see what it says there. Kathy Campbell wants to have exactly 2 daughters. Assuming that boy and girl babies are equally likely, find her probability of success if, in part A, it says she has a total of 2 children. Okay, so what am I looking for? I'm looking for the probability of having 2 daughters. Now I'm assuming we don't want to do this empirically because that means we'd have to go have two kids a whole bunch of times and figure out how many of those we had 2 daughters on. So let's do this theoretically. And if I go back to the definition of theoretical probability, that's the number of ways I can have 2 daughters, which I'll call 2D, over the number of items in the sample space. And to me, right now, that seems fuzzy. That doesn't make a lot of sense to me right now. So what did I tell you a while ago about where to start on a problem if you don't know where to start on a problem? Start with the sample space. So let's list out the sample space for having 2 daughters. Okay, well, I could have a girl and a girl Or I could have a girl, then a boy. Or I could have a boy and a boy. Or I could have a boy and a girl. That's pretty much it, isn't it? If I have 2 kids. Okay. Now that you see the sample space, did this problem just get very simple? What's the number of ways I could have 2 daughters? 1. Out of what's the number of items in the sample space? 4. So if boy, girl are equally likely, you have a 1 in 4 chance of having 2 girls. That's what happened at our house. Okay, now part B of the problem says she has a total of 3 children. So look, the setup of the problem is going to be the same. The probability of having 2 daughters is still the number of ways I could have 2 daughters over the number of items in my sample space. What's going to change is my sample space, which I'll list in red. I'll tell you what, you have 3 kids right there on the paper. You list out the sample space, and then I'll catch up to you and we'll compare notes. Well, if I have 3 children, then my sample space could look like the following. I could have girl, 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 or girl, girl, boy, or girl, boy, girl, or girl, boy, boy. Now that'd be it, having a girl first. If I have a boy first, I could have boy, 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 or boy, boy, girl, or boy, girl, girl, or boy, girl, boy. So did you get 8 items in your sample space? Okay, and the question is, how many of those have 2 daughters? Now, I'm going to assume, well, the problem said she wanted exactly 2 daughters. So we're not going to count 3 daughters. So exactly 2 daughters would be with girl, girl, boy, boy, girl, and boy, girl, girl. So there are 3 ways she could have exactly 2 daughters out of 8 things that can happen total. 3 out of 8. So the moral of this story is, and the value of this problem is, if you don't know where to start on a problem, start with the sample space. Okay, let's work one more problem before we go to break here. That was an example of theoretical probability. Let's do an example of empirical probability by taking a look at example 5. On 581 here, it says, according to the Pocket World and Figures 2009 edition, published by The Economist, the U.S. population at the end of 2006 included 148.2 million males and 152.8 million females. If a person, why is it using the word were? I think that's not proper grammar. If a person were randomly selected from the population in that year, what is the probability that the person would be a male? Okay. Well, we've actually performed the experiment. We actually went out and had a bunch of kids, people, and we know how many are males and how many are females. So the probability of being male will be the number of males, the number of times the event occurred, which the problem said was 148.2, over the number of trials, which really represents the number of people. And the total number of people is that 148.2 million men plus the 152.8 million women, which is 301 million. So according to this problemo, the probability of randomly selecting a man, if you do the division there, is 0.492. About 49% of our population was male. So listen, anytime you use data, like that with some data, to figure a probability, that's empirical probability. Okay? The data actually represents the experiment being performed. Okay, let's stop there. We pause. So if we look at that last problem a little bit, I'd say out of 301 million experiments, that my sample size is large enough to probably feel good about 0.492 being the probability of randomly selecting a male. If we didn't use all of America, let's say we just went around Shawnee College and counted the number of people and counted how many males there were, and we ended up with a 0.492, and maybe that day on campus there were like 400 people and maybe like 197 of them were male, we wouldn't be nearly as confident in our results as we have here with 300 million people. And that's because of what you guys probably know of as the law of averages. But in statistics is what's referred to as the law of large numbers. And basically the law of large numbers says the more times an experiment is performed, the more accurate the results. That's why if you're a baseball fan, and I'm trying to think about who take Mike Trout, probably the best player in baseball now for the California Angels. If he goes the first month of the season and hits 210, nobody gets that worried about it because that's a small sample size. And everybody knows over the course of a season there are ups and downs and peaks and valleys, and by the time he gets 500 at bats instead of 50 at bats, he's probably going to hit right around 300 and probably have around 30 home runs like he always does. So the law of large numbers, the more times an experiment is performed, the more accurate the predictions, or the more accurate the probabilities. Well, the other thing in this section that we want to look at is the notion of odds. So you hear people say sometimes, what are the odds of that happening? What are the odds? And sometimes when they say odds, what they mean is probability. 1 out of 5 chance of raining is really probability. That's not odds. So what is the difference between odds and probability? They're very closely related, but there is a slight difference. The definition that we had for the probability of an event for theoretical probability was number of ways the event can occur over the number of items in the sample space. The definition for odds is as follows. The number of ways an event can occur, call that N of E, over the number of ways the event does not occur. Now that's the odds, also known as the odds in favor of an event. So let me take this off of here. I'd like to have that space back for a minute. So how does that flesh out with what we said a moment ago with the problem we had? We said, what's the probability of rolling a 3 when you roll a 6-sided die? That's 1 out of 6, because there's one way that it can occur out of 6 things that can happen. If you think about that problem in terms of odds, the odds in favor of rolling a 3 is the number of ways the event can occur is still 1. So the top number with odds and the top number for probability are going to be the same. Stay the same. The bottom number is what's different. With probability, you have the total, 6. With odds, you have all the ways the event does not occur. Well, if I rolled a 6-sided die, the number of ways that I couldn't roll a 3 would be if I rolled a 1, or a 2, or a 4, 5, or 6. So that's 5. In other words, to get the bottom number on odds, you can subtract the two numbers on probability. 1 over 6 minus 1, or 1 to 5. Now I'm not going to count it wrong if you give me odds as a fraction like this, but usually odds you see expressed with a colon. The odds in favor of rolling a 3 are 1 to 5. The odds against something, we've been talking about the odds or the odds in favor. The odds against an event is the reciprocal of the odds in favor, or simply the odds. So the odds against rolling a 3 would be 5 to 1. Now don't quote me on this, but I think when you look at betting lines, I think they're expressed as odds against, not odds in favor. Even though they just say the odds are. So let's practice that a few more times. Now, here's what I'm going to say about this, and this is my suggestion. If you get an odds problem, to me, it's easiest to work in this fashion. Find the probability first. Then if you're asked for odds, convert the probability to odds. And then if you're asked for odds against, convert the odds into odds against. To me, that's the easiest. So I always find the probability first and then work from there. Most problems are just easier to think that way in my estimation. Okay. The next problem I'd like to look at then is example 8. I'm on page 584 now. Teresa Cortesini has been promised one of 6 jobs, 3 of which would be intern positions at the state capitol. If she has equal chances for all 6 jobs, find the odds she will get one of the intern positions. So, I'm not going to do that. I'm going to find the probability that she'll get one of the intern positions and then convert that to odds. So the probability of getting one of the intern positions is what? There were 3 of those out of 6 jobs total, which would reduce to a probability of 1 out of 2, or a half. So you guys tell me, based upon what we just said a moment ago, if the probability is 1 out of 2, what would the odds be?
2 to 1.
1 to 1. That's right. The top number stays the same. Number of ways the event can occur, still 1. And I subtract to get the bottom number. 2 minus 1 gives me 1. So the odds in favor of her getting an intern position are 1 to 1. And now, I think this is what you were thinking of, Robert. The odds against, if we're asked for that, which I don't think I was on this problem, but if I was, then I take the reciprocal of the odds in favor. So the odds against would also be 1 to 1. So probability, then odds against. Okay. I also wanted to look at, good grief, I need to do all that. We're going to look at example 9 and we're going to look at example 11, so we'll look at example 9 next. This is on page 584 still. So here we have Bob Barrickman has purchased 12 tickets for an office raffle in which the winner will receive an iPad. If 104 tickets were sold and each has an equal chance of winning, what are the odds against Bob's winning the iPad? So let's find the probability first. The probability of Bob winning is he bought 12 tickets and there were, what was it, 104 tickets total? .12 out of 104 would reduce to 6 out of 52, which would reduce to 3 out of 26. So the probability that he's going to win an iPad is 3 to 26. Now, Tristan and Summer, how would that convert to odds of him winning the iPad?
Would it be 3 to 23?
It would be 3 to 23. Nicely done. Top number stays, subtract to get the bottom. And if the odds in favor of him winning are 3 to 23, then the odds against would be the reciprocal of that, or 23 to 3. Poor Bob. His odds aren't that good. All right, we're going to finish off with example 11 where we're going to reverse the process. Example 11 says in a certain sweepstakes, your odds of winning are 1 to 99,999. What's the probability you'll win? So now we're reversing the process. We're given odds. We're converting back to probability. Yeah, 1 to 100,000. So the top number still stays the same, but now instead of subtracting to get the bottom number, I'm going to do the reverse of that because I'm going back to probability, so I'm going to add to get the bottom number. If you take 99,999 plus 1, you'll get 100,000. So the probability of winning is 1 to 100,000. Okay, so what have we done here? We looked at some terminology. One key term was sample space. We looked at the difference between theoretical and empirical probabilities and their definitions. We discussed briefly the law of large numbers, and now converting from probability to odds and vice versa. All right, for some practice, we're going to go page 585, 3 through 10, 14, 15, 19 through 21, and 56.